exercises 3.4.6 and 3.4.7 using the online tools of the vector field plotter and Desmos. Keep in mind that when you work through these problems, you definitely want to do the parts of the problems that need to be done by hand. And in order to see the handwork that's required for these problems, go back and look in my playlist for the video on the nullclines for competition model. Because in further exercises 3.4.6 and 7, we have 2 more instances of a deer-moose competition model, and I use the example that's in the text to work through that. So you definitely want to use that video to step you through the process that you're supposed to do by hand on paper. And I just want to complement that with showing you some numerical tools that you can use to confirm your answer and to further explore the system in more detail. So here's the link, I just want to note that when you use this resource that we've been using all quarter, you can actually produce a link for yourself by clicking right here where it says link 1 current tab. And if you do click that, you can see that you can copy that link or you can open that link in a new tab. And what it does is it pops up a link that already has your equations typed in. And that's super convenient so that you don't have to go back and type in your equations later. And that's where I got the link that's in the description. See the description of the video where I have a link that already has these things typed in. So if you look at further exercise 3.4.6, which is on page 147, you can see that I have exactly typed in the system that they described there. But when you use this online tool, you have to use X for D and you have to use Y for M. So look at that carefully and see that I've used X everywhere that there's a D on that problem and Y, little x and little y, replacing the variables for D and M. That's one thing that you have to know about this is that they're always referring to the first variable as little x and the second one as little y. The other thing you need to know when you're typing this in is that you have to make use of this asterisk symbol here. You see, if I get rid of this and I just type 0.3x, which is the 0.3d term from before, it doesn't really like it. Well, I can't get rid of what I already did there, but it's not going to really work that well unless you have the asterisks is there. So make sure that you've done that. And where I have the squares, you see I'm using the caret, which is the little symbol that's above the number 6 on your keyboard. And I'm using asterisks between the parameters and the variables, and also between the variables and the other variable. If you get it typed in just like that, you should be good to go. The other thing you want to always know when you're using this resource is that it defaults to the Euler numerical method, but that's kind of the least accurate of all the methods that you could choose. And so you're going to want to either choose something like Runge-Kutta 4 or the Runge-Kutta 3/8 rule. These are more advanced methods that allow us to get more accurate numerical solutions while using the same dt, or h as it is here. And so make sure that you have it set on one of those more powerful numerical methods, and then you can start simulating trajectories just by clicking around in the phase plane here. And as I'm exploring the phase plane of this system, I see that pretty much no matter where I click, all the trajectories are going towards here, which predicts the stable, steady state of 15 X, which in this case are deer, 15 deer, and 0 moose. So it predicts extinction of the second species and a stable level of the first species at its carrying capacity. And those trajectories, whichever is the last trajectory that you clicked, is going to have a corresponding time plot when you click this right here. So definitely, as you're clicking through the trajectories, have fun by comparing the trajectory with the time plot on that tab below. It's a really cool tool because you can see that as I move my cursor around, well, there's a little bit of lag there, but you can see that the black dot in the state space also has a corresponding place for the x and y variables in the time plot, and it's just really nice to be able to match that up. Remember that in the state space up here, time is implicit, so you can't really see what time it is, but you kind of have an idea of the flow because you're following the vectors in the vector fields. But it's really nice to see how that exactly matches up with the time dynamics. Here on this, the x-axis on this graph is time. And the x and the y variables are both described as dependent variables here. So that's really fun. Definitely explore that, because you can see that trajectories pointing towards here are really describing the x variable topping off at its carrying capacity of 15 and the y variable dying out. And you can see that that die out seems to be exponential in its nature. Okay, so it seems like we have a stable, steady state at 15, 0 for this system. The rest of this problem asks you to sketch the nullclines. Well, you should definitely follow my other video and do that part by hand, but you can also do it on Desmos, and it's really fun to compare what we see in this vector field with what we would plot for the nullclines in Desmos. So you see I've also created this little fun Desmos thing, and I'm going to line it up with the state space here, so you can see the state space with the vector field overlaid, and you can also see my graph of the nullclines in Desmos. When I work with Desmos, I want to make sure that I'm color coding the nullclines. Okay, and by the way, you can also save links of things that you created in Desmos, and look in the description of this video in which I've saved this link, and you can play around with this link as well. Okay, so just like I was doing on the board, on my whiteboard videos, I'm using the blue color to denote the D nullclines, the nullclines for the first variable, and I'm using a red color to denote the M nullclines, the nullclines for the second variable. How to change the color is you just click on this little thing up here, and then you're able to pick a color and a style for each one of these things. Okay, so for problem number 6, these are the two D nullclines, and these are the two M nullclines. Remember how we noticed in this vector field that everything seems to be going toward that one spot, 15, 0? When you look at the nullclines on Desmos, you can see that there is a fixed point, an equilibrium point right there at 15, 0. And remember, don't get fooled by the intersection of an M nullcline with itself. There is no equilibrium point where the red meets the red. There is no equilibrium point where the blue meets the blue, only where the red meets the blue. So there's equilibrium at 0, 0, at 0, 5, and at 15, 0. The Desmos part allows me to graph the nullclines, and by the way, you can see that I graphed them really easily for this one. Unlike what I did on the board in my whiteboard video, I didn't even have to solve this one for y. I just factored out an x in the first equation there, and then I just took the other factor and I just set it equal to 0. You don't even have to algebraically solve this for y to be able to graph it in Desmos. It's a really great feature. So this allows me to see the nullclines and how they look and how they intersect, but it doesn't allow me to see the arrows on the vector field. So I kind of have to use this Desmos tool in tandem with this vector field plotter tool so then I can see all the arrows. Now, did you notice how I was choosing all these trajectories in this region up here where we see the vector field is pointing down and to the left? Over here, like we were talking about, the nullclines split up the behavior in the state space into regions of qualitatively similar behavior. And this huge region right out here is where we're going to have everything pointing to the left and down. And we confirm that by looking at the vector fields over here. When you start to do the analysis that you see me do on the whiteboards, and I'm drawing arrows on the nullclines, you'll see that you need to analyze this D nullcline for whether things are going to be pointing up or down. Remember that on a D nullcline, because D is the horizontal variable, the vector field will either be pointing down or up, because the only component that's not 0 is the M prime rate equation. The D prime is equal to 0. That's what defines the nullcline. So how does that match up from what we saw over here in the vector field plotter? Well, look at this. You see this arrow that's almost pointing straight down? And you see all these arrows here where, let me clear it out so you can kind of see it in action again. As I start to click on curves that are inside this region, you'll notice that all these curves start going to the left and then they make a turn. You see where they make this turn here where for just a little moment they point directly down? Here it is again. Here it is again. Each one of these trajectories has something in common. They all have this little knee right here or elbow where they take a turn around, and for just a moment they're just pointing down, straight down. Over here, we would see that as we work through drawing the vector field on top of the nullclines, because if we did that analysis, we would determine that on this blue nullcline for D, the vector field is always pointing straight down. So if you picked a test point that was anywhere along this D nullcline, you would get a component for M prime that's a negative number that corresponds to the vector pointing down. And that's exactly what we see right there. So that's kind of how those two analyses match up with each other. It's kind of cool to see. Now, if you remember from my previous examples on competition models, there were actually 4 fixed points, 4 equilibria. But here, it seems like we only have 3 equilibria. We have this one stable equilibrium point here, and we have we have one fully unstable equilibrium point at 0, 0, and then we have one saddle point, which has a stable behavior just along the vertical axis here, and then it has unstable behavior off of the vertical axis. So this point right here is an unstable but saddle type of equilibrium point. You can see those equilibrium points here in the nullclines, where you see that intersection point there, and there, and there. And then if you're wondering what happened to the 4th point, well, it is there. It's just not ecologically reasonable to consider this point, because you can see that the other point, the place that was representing coexistence in some other competition models, is now lying in the 2nd quadrant, where the 2nd variable is a positive number, but the 1st variable is a negative number. Now that doesn't have any good ecological interpretation, and so that's why we're ignoring this point. However, if we wanted to, we could kind of stretch out this phase plane to include the 2nd quadrant there, and then we would see another equilibrium point. Oh look, it kind of looks stable too. You see how things are tending toward it in kind of a swirlish kind of manner? So that actually might be a spiral sink over there, which is fun to consider for dynamical systems, but for ecologists, negative 20 deer doesn't really make much sense. So that's why we're ignoring that point, but using our tools, we can see that that still exists. Okay, so that was the first model, and matched it up quite nice with the Desmos. And now what I want to do is move on to question number 7 and see how that behavior changes the nature of the nullclines. So you'll notice that I titled this one Further Exercises 6 and 7. And that's because if you look really carefully at the questions number 6 and number 7, they only differ in a couple different ways. The parameter that's multiplying the d squared in the d prime equation changes from 0.2 to 0.5. And the interaction term in the d prime equation changes from 0.5 to 0.3. Those are the only 2 changes. So basically the difference between question number 6 and question number 7 is that this nullcline from question number 6 changes into this nullcline for question number 7. Even though it seems like just a minor difference, just changing 2 of the parameters by a little bit, you can see that it drastically changes the look of that blue nullcline. So again, this bold line, this bold blue line here, is the nullcline from question number 6. And this dashed nullcline is the nullcline from question number 7. And remember how we had that coexistent point that was hanging out over here in the 2nd quadrant where it's not ecologically feasible? As we go on to number 7, that point of coexistence, that equilibrium point here, has now changed. So I'm going to remove the nullcline from question number 6, and this is the visualization for the nullclines in question number 7. And you can see that point of coexistence right there is actually in the 1st quadrant. And you can see that the point that before was 15, 0 has changed quite a bit. Now it's at 6, 0. But this point at 0, 5 has stayed the same. Okay, so how does that change the look of the phase plane or the state space? It's going to change it quite a bit. And I'm just going to pull up the other model. So this is the answer. This is the phase plane for question number 7. And here it is for question number 6. So I'm just going to put them on top of each other so you can compare. This was number 7. Remember in number 7, no matter where I clicked, I always ended up with the death of species 2 and just species 1 hanging out at its carrying capacity. Let's see what happens when I click on the phase plane for question number 7. Oh, look at that. Now it's starting to tend toward this point right here. It seems like it wants to equilibrate at a equilibrium point that represents coexistence, and that confirms what I was seeing in Desmos. Remember, I saw that that equilibrium point moved from the second quadrant into the first quadrant, and it turns out when you really analyze it that that turns into a stable equilibrium point. And the point before that was lying along the horizontal axis that used to be stable in question number 6 has now become unstable. You see, if I try to click nearby, it moves away from that fixed point and it moves towards the coexistence equilibrium point. So the whole entire situation changes, and that really does mean a lot for ecology. Comparing the look of the time graphs here, you can see that time graphs for question number 6 result in let me just click on another one here. So time graphs for question number 6 result in species 1 being at its carrying capacity and species 2 dying out to extinction. Time graphs for question number 2 result in both of the species equilibrating at some non-zero amount, which is represented in the state space as this equilibrium point of coexistence. Now, one thing you got to notice when you're looking at these time graphs is that they don't necessarily start the axis at 0, 0 here. You see how the lowest point on the red is 4.5 and the lowest point on the blue is 0.5. That's just something you really want to watch out for. Make sure that you're reading these axes here because, for instance, if I wasn't looking at these tick marks, I might think that the red species, species number 1, is dying out, but that's an incorrect interpretation. It's just tending toward the value of the equilibrium point here. It's not dying out, it's just that they kind of cut off the axis there so it doesn't go all the way down to 0. Just make sure you're looking out for that as you analyze the systems. And see the description again for 2 links. The first link is going to be giving you access to the phase plane for question number 6. And you can just change that appropriately so that you change the parameters to be for question 7. And the second link is going to be our handy dandy nullcline plotter, in which you can turn on this nullcline and turn off that one, and then you'll see the nullclines for question 6. And then if you turn that one off and you turn on this one, then you're going to see the questions for nullclines. You're going to see the nullclines for question number 7. So again, this is really convenient stuff. It's really fun to use numerics and it's very satisfying. You can do a lot with it, but you also have to be aware of the issues that numerics has, such as very careful graph reading and such as making sure that you're using the correct numerical algorithm. And you also want to do the handwork so that you understand this more conceptually. But I hope that this is useful to you.